Welcome back to PV Online. Today we're going to take a look at how to calculate rates of decay and half-life. So different nuclei have different rates of decay, so we'll want to calculate how long will they be around, how long will they be stable, when will they go. So essentially what the half-life is the time it takes for half of the original sample to, at a time of 4, whatever the unit is, at time of 4, you can see that we have an amount of 50. And that could be 50 nuclei, it could be 50 grams, it's just some arbitrary number amount. Well, to go to the point where you have half of it left, that would be at 25. And you can see that that takes from 4 to 6 seconds. So let's say it's seconds. From 4 to 6 seconds, that would take 2 seconds. So to go from 50 to 25, or half of it, it takes 2 seconds. Now for the next one, if you look at it, to go from 25 to half of that, which would be 12 and a half, you can see it takes another 2 seconds. So what happens is each successive time you just lose half of it. It doesn't go from half and then to 0. So this is going to be an exponential decay. In order for us to make our calculations, we need to have the rate constant. And the rate constant is K. And so for the time, we know what the time is for the half-life, then we can determine that value of K. And so that equation down below, but unfortunately we can't see the half down there. I didn't get the screen right. But you can see that equation that K equals 0.693 divided by the half-life. And that relationship is going to be important to us. So next we want to take a look at a couple examples. Okay, so we have a typical homework problem, and it says cobalt 60, and the 60 just tells you the mass number of your cobalt isotope. It decays with an emission of beta particles and gamma rays, and it's got a half-life of 5.27 years. All right, so I know that the half-life, so the time for half of it to decay, so that's your half-life, and that's going to equal 5.27 years. And it says how much of 3.42 micrograms of cobalt 60 remains after 30 years. So we have a time, so after 30 years, we want to find out how much of that original cobalt 60 is remaining. So the original mass of the cobalt 60 is going to be 3.42 micrograms. Now, what we're going to be doing here, it doesn't matter if we have it in terms of grams, in terms of nuclei, the relationship is going to be exactly the same. And we want to know how much is left. So I put M sub 0 for original, and M, and if you wanted to, you could put a little t to say at some time t, what's going to be the mass that's remaining. Well, I know that there were several half-lives because 5.27 goes into 30 more than 5 times. So I need to find out the rate constant. And the way we find out the rate constant is that the rate constant is going to equal 0.693 divided by the half-life. And in this case, the half-life was 5.27 years. So my rate constant is going to be 0.693 divided by 5.27, and that's going to give me 0.1315, let's say. I tend to keep all my numbers in my calculator until the very end. So I'm going to say 15, and my unit is going to be years to the negative first, because 0.693 doesn't have any units, and we've got the years in the denominator. All right, so we want to find out how much of the cobalt remains. So using the natural log, and I'm going to take the concentration, or the mass, pardon me, at some time t, divided by my original mass, is going to equal negative kT. All right, these are simply going to be plug and chug, and you've probably done these in your math classes before. Rate laws deal with these. A lot of business calculations have to do with exponential functions. So it's now just going to be a plug and chug. So I've got the natural log, whoops, And the mass at some time is what I'm looking for. So I'm going to leave that like so. I'm sorry, it's sloppy. I have a hard time writing on the computer. And the original mass was 3.42 micrograms. All this means is that my answer is going to be in micrograms equals negative K, and my K was 0.1315, times my T, which is 30. All right, the rate constant is years to the negative first, while the time is in years. The years cancels out, which is important because I can't have an exponential function with a unit. So now the main thing that we have to do is we have to get rid of that natural log. And the way you get rid of the natural log is on your calculator, hit the second natural log button, which makes it e to the x. So I'm going to take e to the negative 0.1315 times 30. And that gives me, I'm going to go to the next page. I'm going to rewrite this so it's not so sloppy. So we had the natural log of the mass at some time t divided by the original mass, which we said was 3.42. Now keep in mind this whole thing is in the natural log function, equals negative k, and k at a value of 0.1315. That was years to the negative first, times 30 years, which makes the years cancel. So once I put in the way it looks in my calculator is I'm going to have e raised, and in my calculator it says negative 0.1315 times 30, and that's going to leave me with my mass at some time divided by the 3.42. Well, when I throw that in my calculator, I get 0.01935 equals my mass over the 3.42. So now, to solve for the mass, all I need to do is multiply both sides by the 3.42, which gives me 0.066. Since my original mass, 2, I'm going to round it. Since my original mass was in micrograms, that means my answer has to be in micrograms. And this is pretty much all there is to radioactivity as far as the calculations. So good luck. Bye.